So welcome back. In this video we're going to continue this exploration of trying to figure out how you can tell whether you're at a max or a min for a function of more than one variable. So we started out with the sort of proposal, you'll recall in the last video, that maybe the way to tell is if you look at the gradient and you see the gradient is 0, and you also look at all the second derivatives, second partial derivatives, and see that those are all greater than 0, that would imply that you're a maximum. But then we looked at an example, this example, and saw, hey, that doesn't actually work, right? Because this example actually has a positive second derivative with respect to x, a positive second derivative with respect to y, but it's a saddle point. So in order to resolve that, we're going to sort of take ourselves back to... Sorry, go ahead.
Before we do that, can I look at that picture again?
Yeah, please.
We might want to think about what goes wrong when we were only looking at the x direction, the slice along the x-axis, or the slice along the y-axis. Why was that not enough information? What goes on in the middle here?
Yeah, I mean, it sort of seems like we somehow missed this slice, right?
There's some interaction.
Yeah, so there's something about
missing.
X and Y
that's
missing there. So I wonder, what does this look like, right? So what's the partial with respect to X, Y look like for this? So that's a sort of, I think that's a very prescient question. So should we introduce the Hessian at this point?
I think
let's introduce the Hessian.
Prescient will introduce the Hessian.
Wow, that's that like almost rhymes. All right, so we're going to introduce a thing called the Hessian right now. And the notation here is a little bit messy, but we're going to use it. So here is our notation. The Hessian, first of all, is a matrix. So that's why it has the I and the j components. And the ijth component of the matrix is given by the partial of the function with respect to the ith component and the jth component, right? So if we actually think about this as being a matrix, our sort of diagonals are going to be d squared f with respect to x1 squared, partial of f squared with respect to x2 squared, partial of f with respect to x of n squared, right? And then our off diagonals are going to be things like the partial of f with respect to x1, x2, right? The partial of f with respect to x1, xn, and down here the partial of f with respect to xn, x1, right? Okay, so that's the Hessian matrix. And we should maybe think a little bit about the properties of this matrix, right? So assuming that f is well behaved, one of the things we can see about the matrix is that it's symmetric, right?
Right. So everything above and you reflect in the main diagonal.
So this is equal to that, right? If we reflect across the main diagonal, we get the same
because
things.
We're assuming everything is so well behaved that it doesn't matter which order we take the derivatives.
That's right.